So a relation is what pairs your inputs and outputs. So that a relation is really just more generic than a function. A function is a type of relation. So a relation is just any old function machine, broken or working, right? Is it functional or is it not functional? When a relation is given ordered pairs, the x coordinates are the inputs and the y coordinates are the outputs. Okay? Another way of stating the group of inputs and outputs is to say domain and range. So domain consists of all your inputs, range consists of all your outputs. So we're going to use those terms a lot too. So all of these are relations, but none of them are functions. Okay, so like we talked about up at the front, I want us to identify like why they are not functions. So what about this one? You've got one input right here, which is going to really infinitely many outputs, right? So that cannot happen. That'd be like if you had that machine, you press the button, and then it just started flooding you with all different types of sodas, right? That would be a disaster. Or the greatest day ever. I don't know. But either way, that would not be a function. Is this circle a function? No, for the same kind of reasoning, right? If you just pick any input, you could draw a vertical line. This fails the vertical line test, right? There's two different outputs for that one input. Which input prevents this one from being a function? 0, right? Because 0 is outputting two different numbers. So that's our problem child there. Which input prevents the graph from being from being a function? Which x value produces multiple y values? 3, right? Right here, right? We've got these 2 points that are vertically aligned. That prevents it from being a function. But all of these are still relations. There's still a relationship between x and y. Mm-hmm. So let's talk a little bit more about functions, right? Like what exactly is a function? So this is what we talked about up at the board, but let's just get it in writing here. So a function is a relation with one or more inputs where each input has a single output. Meaning each input or each button that you press only does one thing, not multiple things. Now it's okay to have multiple buttons do the same thing. Okay, that's okay. That does not prevent it from being a function. But each input can only have one output. So this little drawing is just like a funny way to show what a function does, right? It takes your inputs, it takes your x values or the elements in your domain, and it goes through the function machine, and then out comes your output. So it spits out an output, or your y values, or the elements in your range. All of these down below are examples of functions, okay? In this case, there is no x value or no input that outputs multiple things. Each one just outputs one thing, specifically 6. In this graph, there's no 2 points that are vertically aligned. That means there's no x value which is outputting more than one thing. For this graph, same deal, right? No 2 points are vertically aligned. For this set of ordered pairs, looks like there's a missing parenthesis here. There's no x value which is repeated, right? There's no x value that's paired up with multiple y values. So all of these are functions, while all of these are not. So that's going to be part of what we discussed today, is just be able to identify, like, is a relationship a function or not? Any questions so far? Good. All right. So we're going to kind of go through some different forms of relationships and see whether or not they're a function. Okay, so let's compare these two. And the answers are kind of given here, but you know what's different here? In this case, you've got all these different inputs, and I'm going to keep calling them buttons to kind of go back to that analogy I was trying to make earlier. So you've got like these 5 different buttons, and they're all outputting the same thing. So is that a function or not? Yeah, that's okay, right? It's okay to have a soda machine with 5 different Sprite buttons, as long as they're all outputting Sprite. Yeah? In this case, you only have one input, 8, that's outputting all these different things, right? So you press the one button and 5 different things spit out. That's not what's supposed to happen, right? So this is not a function. So let's go through these 4 different ways of showing functions and relations and kind of determine yes or no, like are they functions. So if you're looking at a table, this is showing 2 different relations, and you'll know that the relation is not a function if any x value corresponds to more than one different y value, okay? If any input has multiple outputs. So basically what you're looking for are there any like x values that are repeated that are outputting different y values? So the question is like yes or no, is it a function? So is this first table a function? Yeah, you have all different buttons, right? All different inputs. So that, how do we want to do this? Like color it in, make it nice and, I don't know, yes. Is this one a function? No. Which, button or input or x value is sort of messing things up? 3, yeah. So this is not a function. No. You could also be given a list of coordinates that is basically the same thing as a table, it's just written a little differently. This is called using set notation. So you're just using set notation to list a bunch of points, or ordered pairs. They could be called either thing. So if you're given a set of ordered pairs, it will not be a function, again, if any x value corresponds to more than one different y value. So you're sort of looking for the same thing. It's a little harder to just see quickly because they're not lined up like they are in the table. But you're just looking to see, are there any basically repeated x values? So are there any repeated x values here? Like, are there any duplicated buttons? No. So this is definitely going to be a function. Which x value is preventing this from being a function? 1. Good. Now, when you're looking at a graph, we sort of talked about this already at the beginning, but we are going to use something called the vertical line test. And what the vertical line test does is it tests to see whether or not your relation is a function. And it basically goes like this. If there is any place on the graph where you could draw a vertical line, meaning like up and down, and it can touch the graph more than one time, then it is not a function. So like, is there anywhere on this graph where I could draw a vertical line that touches the graph more than once? No, like you could try like here or here, like none of these are going to hit more than once, right? So this one is definitely going to be a function. The relation will not be a function if a vertical line ever touches the graph more than once. So 2, 3, 4, any time that it's going to touch more than once. So is this a function? No, right? Because you could draw a vertical line, let's say at x equals 1, and it touches the graph twice. And what that's basically saying is that there's one input or one x value or one, quote unquote button that has multiple outputs. Finally, we've got this thing that's called a mapping diagram, where basically it's like a table that's all mixed up. But the arrows show you which x values or which inputs or which elements of the domain are paired up with which y values or the outputs or the elements of the range. So look at the arrows. Now there's something kind of weird going on here because there shouldn't be any arrows pointing to the left because we go from left to right. So let's see, do I have any whiteout? Or You guys are probably not going to have whiteout on hand, so cross out these arrows. There should be no arrows on the left side. It's just whoever made this kind of messed up. So the arrows should be pointing to the right because they go from input to output. So are there any inputs here which go to multiple outputs? Is there any buttons that do two things? No. So this would for sure be a function. If any input maps to more than one different output, it is not a function. So for instance, in this case, which input is sort of breaking the relation and making it so that it's not a function? 3, right? 3 is our problem child here. So this would not be a function. Any questions about how to tell whether or not something is a function? Or does it kind of make sense? You kind of have to practice it a little bit, I get that, but all right, well, let's see if you can figure some of these out. Number 1, we're just trying to determine, is it a function or not? What do you think? Why not? Yeah, so we're going to say no, it's not a function, not a function. And because at x equals 3 has 2 outputs. All right. Now you only need to find one thing that if you're going to say it's not a function, you don't have to list every single instance of what is sort of preventing it from being a function. Like, let's say 2 had 2 arrows coming from it. You don't have to list them both because it's not a function if just one of them is doing that. You can list them both if you want, but you don't need to. Like if you look at number 2, there's a couple of instances where an input prevents it from being a function, right? Like, what are the 2 inputs that are preventing this from being a function? Hey, good morning. Yeah, so which input is preventing this from being a function? Say what? Yeah, 7 and 5. Right? Now, you don't necessarily need to state all of them. It's okay to just state one, because really we're just trying to say why it's not a function, right? So, not a function because x equals 3, or not 3, 5 has 2 outputs. You could also say 7 as well. Any questions so far? All right, so I want to do number 3. I want to do the odds with you together, and then I want to see if you can come up with the answers for the evens. So let's take a look at number 3. What do y'all think? Is this a function or not? Okay, so if it's not a function, why is it not a function?
It is a function.
Okay, well, why?
Because there's something and negative, something are two different numbers.
Yeah, so if you look at all the inputs or all the buttons on your machine, they're all different, right? There's no single button that you can press to have 2 different things pop out. So this is a function. There's no repeated x values here. All right, let's take a look at number 5. You're saying that's not a function? So tell me why.
Sorry, I thought we were on 4.
Okay, yeah. So I'm going to see if you guys can do the evens.
It is a function.
This one's a function?
Yes.
Okay, well, how come? How do you know that?
Because negative 3 and x is 2 different numbers. They're all like
Yeah, basically, like, if you're going to say that it is a function, your reason why is going to be the same every time, right? Like, there's no input that outputs more than one thing. So there's no repeated x values. So yeah, each radio frequency in a listening area has exactly one radio station. What about number 8? Oh wait, I'm going to have y'all do that one. Okay, number 9, is that a function?
No.
No, why? What does it fail? Fails the vertical line test, yeah? So we can just say no, and it fails the vertical line test. Okay, so take a minute and try to do 4, 6, 8, and 10. Say yes or no, and just give like a really brief description of why that is. It is a function or it's not a function? Okay, why not? Which x value is preventing it? Yeah, this -1 business, right? You're listening to country and hip-hop at the same time. Big disaster there, right? No. Okay, there's a repeated x value. Number 6. Is that a function? No, we've got another repeated x value. All right, number 8. Each person is measured for their height. So let's So okay, yeah, what do you think? Yes or no? Or does it kind of depend? What does it depend on, right? Their height, right? Like, so if I had to guess, I would say there's probably 2 people in here that have the same height. Probably. Maybe not, but it's a pretty fair guess, I think. I mean, you're all kind of around the same height anyway, right? So no, 2 people have the same height. Wait a minute. So are we going to say no? Wait a minute.
Because even P has one, even if the stages are different.
Okay, so hold on here, because I like where this is going. Initially what we said was no, because hey, okay, there could be 2 people with one height, right? But that's not really what makes or breaks a function, right? What makes or breaks a function are the inputs having multiple outputs. So what's dependent on what in this case? And that's really where we're going to go with this. Like, what is our x's and what's our y's? What are our inputs and what are our outputs here? So in this case, our input is the person and our output is the height. So you have the person first, you measure them, and then they output a number, basically, right? So can there be a person with 2 different heights? Yes?
No. Depends on what shoes they're wearing.
Well, I'm going to go with no. You can only have one height. It might change over time, sure. But like if I just measured you all right now, I'm not going to get 2 different numbers, right?
Well, tomorrow.
Well, that would be another experiment, right? So let's just to simplify the idea, because yeah, we can find exceptions here and there, but the idea being, I measure all of you, I make a big chart, say Amikit is 5'7"? Okay. Ari is 5'9". You know your height? What is it? 5'8", okay. And so on and so on. Basically, we're gonna like list a name and a height. Each person only has one height. So this is a function. Right? Each person only has one height. Number 10. This one's a pretty easy one once you understand the vertical line test. Yes or no? Is it a function? Yes. Okay. Yes, it passes the vertical line test. Any questions so far? Okay, so we've already briefly mentioned domain and range. Let's just kind of nail down those concepts here. Okay, so the domain of a function is the set of all possible input values, basically your x's, okay? The range of a function, can you see that? Oh, nope, there we go. The range of a function is all of the possible output values, okay? Those are our y values. So one of the things we'll do is sort of write out the domain and range. There's two ways to do that, and I'll try to explain like how you know which way to do it. And that has to do with whether or not a function is continuous or discrete. Okay, a discrete situation is a set of input values that only contain certain numbers. In other words, like if you're looking at a graph, it'll look like a scatter plot. Right? It'll just be like individual points. Okay, so I'm just going to put individual points. Okay, but a continuous function is a set of input values that consists of all the values on the interval. Okay, that's where you have like a line or a curve. In other words, it's like one continuous measurement, right? Like you can see all the values from A to B. So if you ever get a list of values, that will be discrete. If you have like a line or a curve or something that is always changing, that would be continuous. So like for example, if I'm talking about the number of people in the room, that's discrete. There's like a specific number, right? But if I am measuring the temperature of the room, that will fluctuate, right? You can't get from 70 degrees to 80 degrees without hitting everything in between. It can't just jump, right? There's no jumps in a continuous function. So let's run through these real quick and first say whether they're discrete or continuous, and then I'll show you how to write the domain and range. Okay, so number 11, discrete or continuous? Discrete, right? It's just a list of points. All right, they're just disconnected points, basically. All right. Number 12, that's continuous, right? That's a curve, right? It's a line or a curve, and therefore it's continuous. Number 13, discrete, just a list of points, individual points. Number 14, continuous, it's a line or a curve, right? It's just everything in between. Number 15. Continuous. They're connected, right? So it's going to be continuous. And finally, 16. Yeah, that's going to be discrete. Basically, if you have connected points, it will be continuous. If they're not connected, it's discrete. Okay. All right, so the last thing. Yes, sir. Sure. The last thing is to write the domain and range of these things. Okay, so the problem with writing domain and range is it's going to be different depending on whether or not it's discrete or continuous. Because what you're doing is you're listing all of the x values and all of the y values. So for when it's discrete, it's pretty easy. So like, if I want to list all the x values of number 11, I would say x, or here, I'll label it with domain, just so we're clear here. And I'm going to just list all the values so I'm going to use a set bracket here, a little squiggly bracket, and just list all the x values. So what's the smallest x value of those points that are drawn on there? Yeah, 0. So 0, 1, 2, 3, 4, 5 are all the x values. The range consists of all the y values. So what are the y values here? Just pick a point and tell me what the y value is. Yeah. All three of these points share the same y value, right, 4, and all three of these points share the same x value, 3. You don't have to list them more than once, so you could just say the range is just 3 and 4. You're just listing the unique x and y values for domain and range respectively. So let's do the other two discrete ones, and then I'll show you how to write domain and range if it's continuous. So for number 13, the domain, and you don't even have to really worry that they're in order, just list all the x values and be done with it. So I'm just going to go through each of these points. If there's anything that repeats, you don't have to list it twice. If you do, it's not wrong, but you don't have to. And I'm just going to list all the x values here. -4, 1, 4, 7, 10. Actually, those are in order, so that's kind of nice. They don't have to be in order, but these are. The range is all the y values. So 12, 6, -2, -8, -14. Number 16. We've got kind of a lot going on here, right? Domain is going to be, what's the smallest element in the domain? 0. And it's such as 0, 1, 2, 3, 4, 5, 6, 7. Uh-oh, the range is going to be kind of tough here. We're going to have to estimate the range, I think, for a couple of these points. So like, we definitely have 0 in our range. But what does it look like the y value is here, if we had to guess? 0.8. Well, actually, take a look at this. It goes from here to here to here, back here. So I think what this is like 0.75, 0.5, 0.25, and then just 3. So let's go with that. We got 0.75, 1.5, 2.25, then 3. I'm going to run out of room here. So what's after 3 would be 3.75, 4.5, and 5.25. So writing the domain and the range for discrete situations is pretty easy. You just write all the numbers that are contained in the list of x's and y's. Do y'all have any questions about domain and range for discrete situations? All right, so let's talk about continuous situations. The problem with writing domain and range for continuous situations, like let's look at number 12, is that you can't write all the values. There are infinitely many of them, right? Because not only is 0 in the domain, but so is 0.1 and 0.2 and 0.3. When they're connected, it's all of the values in between there. So what we're going to do is we're going to use inequalities to write the domain and range. So what I would recommend you do is draw a little box around the graph, like this. This is going to help us decide the minimum and maximums for our domain and range. So if you look at this box, it kind of shows you like how far to the left and how far to the right the graph goes. What is the smallest value in the domain? Like what's the smallest x value? -3, right? And that's a closed dot, which is important to note. What's the biggest number in the domain? 3. And every value in between counts as well, right? They're in the domain. So the way we're going to write domain for a continuous situation is using an and inequality. That looks like this. X is in between -3 and 3. And so you'll write it just like it'll always be like these less than symbols. It might be less than if you have an open dot, but it'll always be less than, and the x will be in the middle. And then you just put the smallest number on the left and the biggest number on the right. For the range, you do kind of the same thing, except you're looking at the y values. So what is the smallest y value? How low does the graph go? 0. And how high does it go? 3, right? So the range would be from 0 to 3. So you notice how we're writing the domain and range a little bit differently for continuous functions than for discrete ones. Let's take a look at number 14. The strategy, since this is a continuous function, is going to be to box the graph to help you really see what the minimum and maximum values are. All right, so let's write the domain. We're going to have x, and even though they're both less than, like surrounding the x, one of them could be equal to, one of them is not, right? Because we have an open circle here and a closed circle here. So only this one would be equal to also. So what's the minimum and maximum here? It's the smallest and largest numbers in the domain. Yeah, 0 to 3. And actually the range here will be the same thing, except with y, right? Because you go from 0 to 3, 0 to 3. All right, number 15, last one. And I'll give you all your homework. You draw this box around the whole thing so I can see the minimum and maximum a little bit easier. All right, so my domain. What's the smallest? Oh, you got to really look closely. These numbers are very small. What's the smallest x value? X value. So in other words, what's this number right here?
0.
Well, 0's here.
1.
It's 1, right? Because here's 5. And it's really small, kind of hard to see. 1, 2, 3, 4, 5. So this is 1. So the domain goes from 1 to what?
Is it 1, 2, 3, 4?
Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the range would go from what to what? What's the smallest y value? Yeah, negative 20 to, is that 30? Yep, that's 30. So that's the domain and range for that one.